Okay, we are now recording. Shucks, I meant to have opened this already. I'm out of my usual routine, so sorry about this. I usually have this open before I start recording. So now people at home will see me opening all this. Okay, Chapter 5, Analytic Trigonometry. 5.5 is what we're starting today. If the PowerPoint will ever open. And for some reason, I don't know why the projector won't project just because I don't have it plugged in. I mean, that's ridiculous, don't you think? They make me plug it in before it projects. It's crazy, isn't it? Okay. All right, now we're on the right page. We'll start outside of the slideshow from current slide. And this is where we begin. Any questions what we've done so far? Okay. Well, Chapter 5 is still Analytic Trigonometry, and we are in the last section. So at the end of this section, I can give you your test, and if I have it, I have to check and see if it's run off, because I didn't have a chance to take it by there. I was running late at getting over here. But multiple angle and product to sum formulas. Now we'll also have a sum to product formulas, okay? So the objectives of this section: use multiple angle formulas to rewrite and evaluate trigonometric functions, similar to what we did in 5.4. We'll use power-reducing formulas to rewrite and evaluate trigonometric functions. Get an idea? They want to rewrite and evaluate trigonometric functions. And we'll use half-angle formulas to rewrite and evaluate trigonometric functions. So we got to come up with these. We talked about multiple angle formulas. We haven't done power-reducing and half-angle, so those are going to be new for this one. Then we'll use product to sum and sum to product formulas to rewrite and evaluate trigonometric functions. And we'll use trigonometric formulas to rewrite some real-life models. And that will basically end us with Chapter 5. So let's first look at multiple angle formulas. Okay? In this section, we will study 4 other categories of trigonometric identities. Okay? The first category involves functions with multiple angles, such as sine Ku and cosine Ku. Now, we did some of those in solving equations, and we did some of those when we were doing how it changes the periods and that kind of stuff in graphing. But we haven't actually come up with any work with the functions doing this and identified some identities with that. The second category involves the squares of trigonometric functions, such as sine squared u. Even though we've done that and we've used that in identities before, we'll come up with some new approaches to that. The third category involves functions of half angle. So this is multiple angle, this is fractional angles, specifically half angles, such as sine of u over 2. The fourth category involves products of trigonometric functions such as sine u cosine v, which looks sort of familiar. That was part of sine of a plus b, right? Or u plus b, okay. And we'll go from there. You should learn the double angle formulas because they are used often in trigonometry and calculus, okay? And guess what? I don't believe in memorizing formulas. If you like memorizing them, go on and memorize them. But what I like to do is relate them to what we already know. And what we already know is that I've got to get my pen color set up, okay? You remember, don't you, what sine of a plus b is? We may not have used a plus b, but you know what I'm talking about. What would that be? Remember that one? The sum angle formula. Sine of a cosine of b plus cosine of a sine of b. You got it. Okay. You know, I started to do it and then I changed my mind. I'm going to go back and change these just because I thought it would be simpler doing this, actually simpler doing it the other way. Let's not call them A and B. Let's call them U and V. U and V. U and V. U and V. Okay? Yeah, you know that, right? Nothing new. You worked with it so much, you know it by heart, right? Good. All right. Now, here's a supposition for you. What if U is equal to V, or V is equal to U? What would this be then? Sine of U plus U, which is 2U. Happy birthday to you. Happy sign to you. Okay, you know that one, right? And then this would be sine U cosine U, if V is equal to U, right? Plus cosine U sine U, if V is equal to U, right? So guess what that is? Sine of 2U is equal to, here's a sine U cosine U plus another sine U cosine U. That's 2 sine U cosine U. And that's exactly what this is. So it's not a memorizing something else. It's just plugging the one you already know, putting U equal V, and you get it right there. Okay? We can do the same thing for cosine 2U. Okay. What is cosine of U plus V? Do you remember it? Cosine U, cosine V, minus, even though that's a plus, this is a minus, sine U, sine V, right? And what, again, if U is equal to V, this becomes cosine 2U, right? If V is equal to U, that's U plus U is 2U. And this would be cosine U, right? Minus sine U, sine U. What is cosine U? No, it's, they're multiplied. Cosine squared U. So that would be cosine squared U minus sine squared U. And that's exactly what they've got there. Okay? But they've got two others. Now, where did they get those? Can you tell me another definition for sine squared? Think Pythagorean theorem. The Pythagorean identities. Sine squared U. Remember Pythagorean identity? Plus cosine squared U is always equal to 1. So let's subtract the cosine squared from both sides. And that gives you sine squared U is equal to, these go away, 1 minus cosine squared. And you probably use that enough you almost remember that anyway, right? So instead of writing sine squared U, we'll put 1 minus cosine squared U right up here. So this would be, well, in fact, right under here, cosine squared U minus 1 minus cosine squared U, right? But that minus out in front, well, if you distribute that inside the parentheses, that would be cosine squared U minus 1 minus a minus is plus cosine squared U. Now we got 2 cosine squared U, so that's 2 cosine squared U minus 1. Ding! There we have that one, right? Now, so we got 2 different values for cosine squared u, identities for cosine 2u. Yet we still have another one, because just like sine squared u is 1 minus cosine squared u, similarly, cosine squared u is 1 minus sine squared u, right? Because you just subtract sine squared from both sides, and you get that, right? Now we put that instead of this one up here, and that would be 1 minus sine squared u, that's cosine squared u, minus sine squared u. Well, that is 1 minus 2 sine squared u. Ding! There's that one. So you see that's how they get this. So here's 3 different identities that cosine 2u can be. Okay? Which is pretty flexible. You can get in terms of sines and cosines. You can get it in terms of cosines alone or sines alone. So whichever way you need it, choose the one that fits best. Okay? Now, what would be tangent 2u? I think it's easiest to go with the tangent u plus v again. So I probably need to erase some so I have room to write. Is it okay to erase? Okay. Let's erase all that ink. And let's talk about what tangent of u plus v is. You remember that one? I don't use that one as much. What is that? Tangent u plus tangent v over one minus tangent u tangent v. That's what it is. You can flip back a few pages and find that. Okay? Okay. Okay? Now, my most favorite question in this section is, what happens if u is equal to v? What would that be? This would be on the left, would be tangent of u plus u would be 2u. And that would equal tangent u plus, if v is equal to u, what's tangent v? Tangent u again, okay? Divided by 1 minus tangent u stays tangent u, but now tangent v also becomes tangent u, okay? Well, that becomes 2 tangent u over 1 minus tangent squared u. And that's exactly what we've done there. So, do I sit down and memorize these? Nah. I just try to remember the ones I already know, sort of mentally plug them in, and basically you get this. It's not that hard. Just doing that little trick, saying u equal v. If you know what tangent or sine or cosine of u plus v is, then you know what it is for sine, cosine, or tangent to u. Okay? So there are, you might say 3, but then you might also say 5 new identities. 1 for sine, 1 for tangent, sine 2u, tangent 2u, and 3 for cosine 2u. Just use the one that fits your problem the best. Any questions on that? Okay, good deal. All right, I believe we're coming upon example 1. Now the question, is this the same as the one in your book? Huh?
Multiple angle equation.
Solving a multiple angle equation. Is it 2 cosine x plus sine 2x equals 0? Okay, same one. Okay, how would you approach this? Okay, we start with the 2, good start, times cosine x. We don't want to change that. That's about as simple as you can make it. But we do know an identity for sine 2x, and what is that? sine 2x. In the book it says sine 2u, but just change the u to an x. And what is it? It's 2 sine x cosine x. Great. Is equal to 0. Right? Now, you still have two functions in there. However, there's a really easy thing we can do. Split them up by factoring. And how could you factor that? Take out a 2 cosine x from both terms. So that's a 2 cosine x. What's left of the first term? 1 and 1 alone, plus sine x and sine x alone. And that's equal to 0. Okay? So now we can, since we have zero product principle, we can say, what's that? Yes, 2 cosine x is equal to 0, or 1 plus sine x is equal to 0. Okay? Now, that first one, what can we do to that? Because this is an equation, we can divide away our 2, can't we? Right? That becomes 1, and that stays 0. Oh, that's nicer. So cosine x equals 0. And what values of x makes cosine equal to 0? Now, they didn't give us any limitations on your domain, so we'll do the general formula. What values of x would make cosine x equal 0? Where is it? All of your half pi's. You're absolutely right. So that would be x equal pi halves. And the thing is, these are evenly spaced. Well, yeah, evenly spaced. A pi halves here, a 3 halves pi here, a 5 halves pi here, 7 halves pi, 9 halves pi, negative pi halves, negative 3 halves pi, negative 5 halves pi. They're all 0, so they all differ by pi. Most of the time, cosine we would use 2 pi, but because you have 2 zeros in every period, one here and one there, then the periods are exactly, the zeros are exactly pi apart. So this will be plus n pi. Okay? Now, how about that second equation? What would you do there? So 1 from both sides of that equation, and that gives you sine x is equal to negative 1. Now we ask ourselves, what values of x, when you take the sine of it, would give you negative 1? 3 halves pi, exactly. So x equal 3 pi over 2. Okay? And that's the only one in any period, but because sine has a period of 2 pi, you plus 2n pi. That gives you all of them. You would have said 2n pi here, except that those zeros are exactly pi apart. So you just say plus n pi. You could say pi halves plus n pi and 3 halves pi plus n pi, or 2n pi. But why do that? They're exactly pi apart, so just make them that. The book does it the other way, okay? Except, notice here, the 3 halves pi shows up down here too, doesn't it? Yeah. So guess what? We don't need that. We've already included those here. So basically, it's pi halves plus n pi. They split it as pi halves plus 2n pi and 3 halves pi plus 2n pi. But guess what? The 3 halves pi and 1 half pi are exactly pi apart. So all these are exactly pi apart. Yeah, they don't show the period, but sure enough, they're very evenly spaced there at n pi. Okay, Now you can write it the way the book does if you want to. All right, there is a checkpoint there, and good idea to do that as soon as you can later. Well, we've done it. Let's see how they did it. And I'm sure they did it the other way. So let's see what they did. Began by rewriting the equation. Yeah, that was so much fun to rewrite that equation. So that involves functions of x rather than 2x. You have to have the same innermost argument. So let's get it all in terms of x. Then we factor and solve. So they told you everything they're going to do. They start by rewriting the original equation. Good for them. I could have done that if I didn't want to. So 2 cosine x is perfectly fine. It's already in terms of x. But to get this in terms of x, we write the double angle formula, which is 2 sine x cosine x. That's what sine of 2x is. Okay? That's done. Then we can factor out a 2 cosine x, just like you did, leaving us a 1 plus sine x. And then we set each of those equal to 0, zero product principle. 2 cosine x equals 0, and 1 plus sine x equals 0. Well, the x for the first one would be every half pi. This is in between 0 and 2 pi at pi halves and at 3 halves pi. And the other one, the sine equal negative 1, they left off that step, but that's how they got there, is 3 halves pi. Well, you see the 3 halves pi duplicate themselves. So no reason to write them twice. If you did pi halves plus n pi, that's going to give you 3 halves pi, your 5 halves pi, your 7 halves pi. So you'll get the half pi's and you'll also get the 3 half pi. So, but they write it out this way: pi halves plus 2n pi and 3 halves pi plus 2n pi. Where in reality, if you just said pi halves plus n pi, you got them all. Okay? So you can either do it their way or my way. And it says verify them graphically. I wouldn't do the complicated one, though you could do that on a graphing calculator. But when you got it to this form, and you got cosine x equals 0, you know cosine x starts at 1, 0 at pi halves, negative 1, 0 at 3 halves pi, 2 pi, 5 halves pi. So there's your zeros there. They're all pi apart. And if you did the sine on the same thing, it's 0 here, 1 there, 0 here, and minus 1 here. Well, that's the same place where cosine is 0. So that shows you, yeah, the 3 halves pi shows up in both things. So just do these zeros here. You got the other ones, and it works. Okay. I think graphing helps you see some of the solutions a little better. All right, they skip example 2 and 3 and maybe more, so let's us do example 2. Now again, we'll check and see if it's the same. Use the following to find sine of 2 theta. They like to change the variables regularly. Cosine of 2 theta. And tangent of 2 theta. Okay? And here's what they're going to tell you. Cosine theta is equal to 5/13. Okay? And we're also going to be sure we keep theta in between 3 halves pi Now, what does that bottom thing say? The last thing says. Where are we, Waldo? Yeah, where are you? The first quadrant is between 0 and pi halves. Fourth quadrant, you're absolutely right. That's between 3 halves pi and 2 pi again. You got it. You're in the fourth quadrant. Now, to answer me this, is cosine positive in the fourth quadrant? All students take calculus. Yes, cosine is positive there, so our problem makes sense. Always good to make sure the problem makes sense. Okay. Now, you got several things you're going to need to do and I'll let you decide what order you want to do them. What you want to do first. Got a what?
Make a graph.
Okay, I sort of like that idea if I'm thinking the same thing you are, or if you're thinking the same thing I am. What kind of graph are you wanting to make? A circle? Okay, I like that thinking too. Whoa, my circle stinks. It's not quite centered right, but you get the general idea. Okay, my circle's pretty good. My coordinate lines are pretty lousy. So I'm going to erase the coordinate lines. Ooh, I was going to erase the coordinate lines, but they didn't erase. Well, it's still not erasing. There we go. That's one of my better circles, so I didn't want to lose it. Let's see if I can draw better coordinate lines. Whoa, messed that one up. I got my vertical okay. Let's see if I can improve that. Ah, there we go. I got the horizontal. Not too bad. One of my better circles, and it's pretty lousy, but it's one of my better ones. Okay, why did you want to do that?
Because it tells us where we're going to start in the fourth quarter, and we already know we start there, right?
Okay.
And, identify sin theta when I say in the fourth quarter.
Okay, not bad. So you know you're in the fourth quarter, got that part. And what else you know? What is cosine in terms of?
Cosine is positive.
Okay, you know that. But in terms of x, y, and r, what is cosine?
Cosine is R.
X, y, and r. Remember back when we identified those things? Cosine is always the, okay, in terms of adjacent, opposite, and hypotenuse. Cosine is? Caught another hen.
Opposite over.
Not opposite, that's
Hypotenuse over. Opposite.
yes, that's some old hen. That's the opposite is with sine. So it's adjacent over hypotenuse. Okay, in terms of x, y, and r, what is your adjacent and what is your h? Your hypotenuse. Think kind of reference angles here. Remember those? I'm going to cheat a little bit, and I might not be correct, but sort of. There's our theta, right? Fourth quadrant. Okay. What? And I'll go on and do this too. Okay. Now, that little triangle, that's our theta, but remember we called this theta prime. It acts the same way as theta does. Okay? So, what is your adjacent side? By the way, I guess I'll write this in too. This is x, this is y, isn't it? And guess what your r is? Hypotenuse, exactly. So this is your r. So in our problem, since this is x over r, your x must be 5, but your r is 13. Yuck. That means I have to have not a unit circle here, but a 13 circle. So here's how I go about making my 13 circle. Now, I almost want to erase everything. I think I will, just so it won't be as confusing, okay? But you got the general idea why I put it there, right? Okay. I could have left that maybe. Okay. If I try anymore, I'm going to erase everything, so let me not do that. So I need to split that up into 13. Well, half of 13 is 7, so we'll call that 6 and that 7. Half of 6 is 3, and then you got a 1, 2 in between there, a 4, 5 in between there. Halfway between 7 and 13 is 10, and you got a 8, 9 there, and 11, 12 there, and there's 13. Now that's not very pretty, but it sort of does the deal. Let's do the same thing here, halfway down here between 6 and 7. Halfway to 6 is 3, 1, 2. Oops, that's not very good. And between 3 and 6 is 4, 5. And halfway between 7 and 13 is 10. And you got a 8, 9, and 11, 12. Okay, so there's my thing. Now, our x value we saw from here is 5. 1, 2, 3, 4, 5. There's my x. Okay? So mine was way off. If you drop this on down here, there's your r. R is 13. So here's your x equal 5, and here's your r is equal to 13. Okay? There's our angle theta then. I left the theta in there. So mine wasn't very good. Okay? Do you see that? Now, is that what you wanted to do when you were talking about drawing the picture? Okay, we've done it. What does that tell you? How is that useful at all? Is it?
I got X, I got R.
We don't know why, do we? And what would y be? How can you get that?
A squared plus B squared equals.
You got it. Pythagorean theorem. A squared plus b squared is equal to c squared. And in our problem here, what are those representing? X squared plus y squared is equal to r squared. You got it. Okay? That, by the way, is the definition of a circle. Our circle happens to have a radius of 13. So this would be x is 5, so 5 squared plus y squared, which we don't know and looking for, is equal to 13 squared. Right? 5 squared is 25 plus y squared is equal to, what's 13 squared? Anyone know?
$169.
169. And then what do we do? You're looking for y. So subtract the 25 from both sides. And what does that give us? Y squared is equal to 144. So what would y be? 12. You're absolutely right. Except that your y here is negative, so that would be a negative 12. Y is equal, you see y? In the fourth quadrant, y is negative. Right? And look at my picture here. I mean, it's not too bad. There was 12 right there. Not too bad. Of course, I can draw a straight line either. That's right where it's supposed to be, right? Yeah. All right. Well, the wonders ever cease. Okay. Now, how does that help us any? See, that's why I wondered where you wanted to start. Perfectly okay to start here, but you really, I mean, it's not real clear why we did all that. I know we're going to use it, but where I'm not too sure until I come here. What is sine of 2 theta anyway? That identity? Remember it? This is what we're looking for. What was that identity? 2 times right? Sine of 2u is sine u 2 cosine 2 sine u cosine u, right? So sine of 2 theta would be 2 sine theta cosine theta, right? Got it? No.
I don't get that part.
Okay. Look back at your double angle formula on the previous page, right? 2 sine u, no, I'm sorry, sine of 2u is equal to 2 sine u cosine u. Well, this is sine 2 theta, so instead of that u, you put theta. Sine 2 theta is 2 sine theta cosine theta. Okay? All right. Now, that's what we're looking for. And I know what 2 is. It's 2. Okay? That's easy enough for me to do even. Okay? And I know what cosine theta is. They gave us that. That's 5/13. What I don't know is what sine theta is, or do I? From here, what is sine theta? We said cosine theta was x over r. What is sine theta? No, that would be secant theta. It's reciprocal. Sine theta would be opposite. How much is opposite here? I didn't write it. I started to write it, but I didn't. Minus 12. Right? We just calculated it down there. Y is equal to minus 12. Right there it is. So your sine theta is y over r. So the sine theta then is minus 12 over, same r, 13. And by the way, r's are always positive, right? The radius is always positive. Okay? So here we have what sine 2 theta is. Okay. Now I'm going to do it maybe a little strangely. I'm first going to figure out my sine. You have 3 factors. One of them is negative. Answer is going to be negative, right? 2 times 5 is 10 times 12 is 120. And 13 times 13, we've already done that once, 169, right? There we have what sine 2 theta is. Yay! Now,
12 theta.
say again?
Is it over 169?
Okay, yeah, because this is 2 over 1. So I multiply my numerators together and multiply my denominators together. Right? Because 2 is just 2 over 1. Or you could do it this way. This would be minus 60 over 169. Twice that is minus 120 over 169. Either way you want. I just find it easier to make 2 times 5 is 10 times negative 12 is negative 120. Okay. Now what you think we're going to do next? They also ask for cosine of 2 theta. Right? There are 3 things they asked for. Sine 2 theta, cosine 2 theta, and tangent 2 theta. We've done sine. Let's do cosine.
Cosine is just going to be
What's that?
at the reciprocals of each other.
No, that's sine and cosecant and secant and cosine. They're reciprocals of each other. Don't get those crossed up. Cosine 2 theta, we also have a half angle formula. I mean a double angle formula. Now you could also do the Pythagorean theorem, but I just assume not. Pythagorean identity, it'd be a lot of work. This way I think is a little easier. What is your identity for cosine 2 theta? Remember, cosine, you have 3 of them. You get to choose which one you want.
We got 1 minus 2 sine squared. And we'll do that one.
You could use any one of them, but frankly, here's my little gut feeling on it. One of them was sine squared and cosine squared. Cosine squared minus sine squared, right?
Yes.
Well, you got cosine, we calculated what sine was, okay? But what if we made a mistake with sine? I don't want to use that. Another one, I think the one you said, is 1 minus sine squared. Well, again, you're using the one we calculated. What if we made a mistake? We make a mistake here too. But that middle one, cosine, 2 cosine theta minus 1, the cosine theta, we did make a mistake in. They gave it to us. So that's the one I want to use. Any one of them will do, but that's the one I'd rather use. That would be, this is 2 cosine theta minus 1, isn't it? Or is it squared? 2 cosine squared theta minus 1, right? Okay, and we know what cosine theta is. That's 2 cosine theta is 5/13. They gave it to us. We don't have to guess. We don't have to say, I hope we were right. They gave it to us. They better be right, okay? You're going to square that and then subtract 1 from your answer. Okay, so let's do the squaring first. Be 2 times, what is 5/13 squared? $25 over, wait. Yeah, that's we've done it a couple times. 169 minus 1. Well, 2 times 25 is 50 over 169 minus 1. 1 is 169 over 169, right? And this would then be minus 119 over 169, right? If I did my math right. Now, our last one is tangent 2 theta. Now, you have at least 2 ways you can go on this. Okay? Here's one way. What are you thinking? Go to the formula? Okay, you could do that. Then you would have to use your little triangle here, which you were smart to come up with, and do what tangent theta would be. Tangent theta would be opposite, which is your y value minus 12 over adjacent, which is your 5, and then you have to do that, and you have to square, you have to do things there. Okay? So that's one way you could go. Time out. Don't we also know that tangent 2 theta is sine 2 theta over cosine 2 theta? From our ratio identity, or quotient identity. That, I think, will be a little easier. This is going to be sine 2 theta over cosine 2 theta. And our sine 2 theta is minus 120 over 169 over your cosine 2 theta, which is minus 119 over 169. Now that looks a little complicated, but a couple things do get pretty simple here. Take a look at this. Minus over minus becomes plus. Okay? You can multiply numerator and denominator by 169, because 169 over 169 is 1. That's perfectly legal. This cancels that one out, or divides that out. That divides that out. So you have 120 over 119. Ah, there we have it. Now, the next little thing that I like to do, the book doesn't do it, but I like to do it, is I think to myself, where are we, Waldo? They told us this was our theta. Cosine theta is 5/13. You're in the fourth quadrant. Down here, we figured out where that was. 5 is adjacent. 13 is your hypotenuse. So you're down here, there's your angle. What we're looking for is 2 theta. Well, 2 theta would be this much, which if you think of that, that's 1 quadrant, 2 quadrants, 3 quadrants, plus a little bit. So let's do a little bit more, and then do 1 quadrant, 2 quadrant, 3 quadrant. Where do you wind up? Third quadrant. And what is the sine in the third quadrant? Negative. What's cosine in the third quadrant? Negative. And what is tangent in the third quadrant? Positive. Remember, tangent, positive, positive. All students make positives. So tangent, positive. Now that doesn't tell you your numbers are right, but it sure tells you your signs are, and you're in the right ballpark. And I think you're right, absolutely. Bless you. Let's see how they did. They did, they did it the long, hard way, didn't they? But they still got the right answer, good for them. Okay, they did sine of 2 theta, just like we did, and got negative 120 over 169. Good for them. They did cosine 2 theta, just like we did, using that formula that gave you using only cosines. You could have used either one or the other. You knew them both. Okay, and that gave you negative 119 over 169. And then they worked really hard to get the tangent 2 theta using the formula, and we were just plain lazy and just divided sine by cosine and got the same answer they did. Isn't trig beautiful that way? As long as you do right steps, you can get the same answer, right? Just do the right steps. Okay. There is a checkpoint there, and that's well worth a do too. Okay? Now, the next one. We just are learning about our double angle formulas, and what are they asking us to do? Derive a triple angle formula, right? Well, how can we do this? How can we do sine of 3x? That's what they're asking us for in terms of sine of x. This is ITO, meaning in terms of sine x. Okay. How in the world are we going to approach that?
We're using the same formulas from.
Okay, except those are 2 x's there, right? So how can we get 3x out of 2x, or 2x out of 3x? Here's a little hint. I'll ask you a question. Isn't sine 3x, yuck, I can't write. Isn't 3x the same as x plus 2x? Isn't that 3x?
Yes.
Yes, it is. And we know the sum angle formula, don't we? What is it? Sine, okay, let's start with sine x, cosine 2x. Now, they may have done theirs a different way, but we'll come back and get it that way too. Plus cosine x sine 2x. So you see it comes out the same way. Okay. Now, that's not in terms of sine x. These are in terms of x, but these are in terms of 2x's. But guess what? We know a formula for this now. This we can turn back on that page and do it. So what would this be? Leave the sine x alone. Sine x. What is cosine 2x? In terms of sine. Cosine 2x in terms of sine x. That's the third one, isn't it? Okay. Use the third one of those. 1 minus 2 sine squared x. Right. Okay. Plus, we'll leave cosine x in there for now. And what is sine 2x? You can do it. Go back and see. Sine 2x is 2 sine x cosine x. Perfect. Okay? Now, I may have chosen poorly here, but let's see what we got. This will be sine x, that's sine x times 1, minus 2 sine cubed x. It's still in terms of sine x, it just happens to be cubed, right? Okay? Plus, this will be 2 sine x cosine squared x, right? Oops, I don't need that parentheses. Do I? Okay. Now, everything is hunky-dory except this is not a sine x, it's a cosine. We want it in terms of sine x. So is there any way we can get a cosine squared to become a sine? Pythagorean identity, you nailed it right on the head. And how does that go? Cosine squared x is equal to 1 minus sine squared x. Remember? Cosine squared plus cosine is 1. Subtract sine squared from both sides. You got cosine squared x equal 1 minus sine squared x, right? Okay, so now this will be a sine x minus 2 sine cubed x plus 2 sine x times 1 minus sine squared x. Okay? This will be a sine x minus 2 sine cubed x plus 2 sine x, right? Minus 2 sine cubed x, right? We got it? Okay, we can combine these like terms, and that'll give us 3 sine x, and combine these two like terms, and you get minus 4 sine cubed x, sine x cubed, right? There, we've done it. We've calculated sine 3x in terms of sine x's only. Very good. Nicely done. Okay? Make sense? All right, good deal. All right, that was example 3. And now they say on your checkpoint, do cosine 3x. Oh, that looks like so much fun. All right. So let's go to the top of the next page. I think we've already done that. Yes, to our power reducing formulas. Okay. Now, I sort of don't like for them to just spring things at us like this without telling us how they did that. Do you? No, let's not like them like that at all. But what I wanted you to think about was this. Okay? Look at this formula right here. Cosine 2u is equal to cosine squared u minus sine squared u. Now what does that look, especially that side, look a lot like? But not quite. Got a sine squared in it and cosine squared in it. What else has a sine squared and cosine squared in it? Pythagorean identity. You're absolutely right. So let's go back here and start with it. In fact, let's do it right here. Why not? I'm going to erase everything else on the screen. Is that okay? Okay. Now I'm going to write, I'm going to write my Pythagorean identity first. I'll do it right here. No, I'll do it down here. But I'm going to do it a little backward, but it's okay. Cosine squared u plus sine squared u. That's the same as sine squared plus cosine, right? Squared, okay. That's equal to Pythagorean identity. It's always equal to sine squared plus cosine squared. Cosine squared, 1. That's equal to 1. And here we have a cosine squared u minus sine squared u is equal to cosine 2u. I just reversed the order of the equality. But that's fine, right? Okay. Now, what reaches out and smacks you in the face on that one? What happens if you add these two equations together? You lose the sine squared u, right? So let's do it. Add those two together and you get 2 cosine squared u. These disappear, is equal to 1 plus cosine 2u. Right? And let's just divide everything by 2. And now we have cosine squared u is equal to 1 plus cosine 2u divided by 2. Right? And look, if you've got your page turned to the one with power reducing formula, look at the middle one there. Cosine squared u is equal to 1 plus cosine 2u over 2. That's how you get it. So I don't memorize that thing. I know I can come up with it. Okay? And what's this doing? Here you have cosine squared. Over here you have cosine to the first power. It's to a double angle, but at least it's to the first power. So that's a power reducing formula. Okay? Now we're going to do almost the same thing using these same two equations, except this time we're going to subtract, not add. We're going to subtract this equation from the top equation. Okay? So that will be, when you subtract them, cosine squared u minus cosine squared u is 0. And then this will be sine squared u minus a minus sine squared u is plus sine squared u. So that gives you 2 sine squared u, right? And then is equal to 1 minus, because you're minusing, cosine 2u. And now all you have to do is divide by 2. And now you've got a reduction, a power reducing formula for sine squared. Sine squared u is 1 minus cosine 2u over 2. Wow, we have so many forms for sine squared u. Sine squared u is 1 minus cosine squared u, or 1 minus cosine 2u over 2. Wow, lots of different forms. Okay, now the question comes, can you do the same type of thing with tangent squared u? And I would say yes. And I'm going to cheat again and do it the cheap way. Okay? Because tangent squared u is sine squared u over cosine squared u, right? And sine squared u is, where was it? Here it is. 1 minus cosine 2u over 2 over, and cosine 2u was 1 plus cosine 2u over 2. Well, you can multiply numerator and denominator by 2 because 2 over 2 is 1. And that gives you simply 1 minus cosine 2u over 1 plus cosine 2u. So notice all three of these power reducing formulas, you reduce a sine square to something in terms of cosine 2u. You reduce a cosine square into something in terms of cosine 2u. And you reduce a tangent square into something as a function of cosine 2u. You lose the sines and tangents, but you have reduced the powers. So let's go back and see if they got the same thing. We don't trust them because they're sort of tricky sometimes. Oh, look at that. They got them all three right, didn't they? Okay. Sine squared u is 1 minus cosine 2u over 2. Cosine squared u is 1 plus cosine 2u over 2. And tangent squared u is just this one over this one. These cancel out. Well, but yeah, pretty easy. All right. Good deal. All right. Sadly enough, we're just about out of time. Now, we got started a little late. You want to do a little bit more or just hang it up? One. Okay. Let's see about example 4. Yeah, I like the idea of doing the example. Okay. Rewrite sine fourth x in terms of first powers of cosines of multiple angles. Okay. Sine fourth x. Okay. Now, our power reducing formula only dealt with sine squareds. So how are you going to do that? Okay, pretty close. You rewrite this as sine squared x squared. Isn't that sine fourth x? Yes. And we know what sine squared x is, don't we? We just did it. Look at the top of the page. 1 minus cosine 2u over 2, but now we're going to square that, right? Okay? Now, not too hard to square that numerator, you just have to take your time, right? That would be 1, right? Minus 2 cosine 2u, right? Plus cosine 2u squared, right? When you square a binomial, you square the first, twice the product of the two, and square the last, right? And that's all over 4, right? Because you got to square the denominator too. Okay? Except it said in first powers of cosine. Here we have a second power of cosine. But guess what? Yes, we can use a power reducing formula for cosine. Now we're very happy with the 1 minus 2 cosine 2u. Those are fine. Okay? It's just this last part. We want to reduce that power as well. Reducing a cosine squared. What does that become? 1 plus cosine of 4u. You got it right, over 2. And all that is over 4. You see that? It's double this angle. This angle is 2u, that becomes 4. Okay? Now, just to clean that up a little bit, this is going to be I'm going to string it out. 1 over 4, that's this 1 over that 4, minus, and this 2 over 4 is going to be cosine 2u over 2. You okay with that? That's an ugly 2, but let's see if I can clean that up a little bit. It's just minus this over 4, the 2 that goes up, that 2 cosine 2u. Okay? Yeah. Now, this next part is going to take a little bit of effort. Plus, what you have here is 1 plus cosine 4u over 2 over 4, right? Well, this last over 4 you could write as times 1 over 4, right? Okay, so I'm going to change that, drop that, and rather than dividing by 4, we multiply by 1/4. Okay, Now this becomes 1/4 here minus cosine 2u over 2 plus, this is going to be 1/2 times 1/4 is 1/8, right? This is 1 over 2 times 1/4, okay? Plus, and this will be a cosine 4u over, now wait, I did something wrong there. You let me get away with it. You shouldn't have done that. This needs a 2 in there, doesn't it? No, it doesn't. No, it doesn't. I was right. You were right. Okay, sorry. I got crossed up. Okay. I lost my seat. I think we're okay. And this will be cosine 4u over 8. Okay. Now 1/4 plus 1/8 becomes 3/8, right? Minus cosine 2u over 2 plus cosine 4u over 8. I hope we got it right. Let's see if we did. Okay. They factored out at 1/8. We could do that. And that would leave you a 3 here and 4 minus 4 cosine 2. Is it x? Where did I get u's? Look at you. You let me get away with the u's there. Those are x's.
Well, I know what you mean.
Yeah. Every one of those is an x. What's that?
You like you better than you like me.
Yes, I like you. No, I'm just kidding. Okay, I do, but never mind. This is x, that's an x, and that's an x. This is an x, that's an x. There's an x, 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 and there's an x. Yeah, I think we got it right. If you factor out the 1/8, that gives you 3 minus 4 cosine 2x plus cosine 4x. Got it.
They got 3 minus 1/8.
Okay, yeah. What they did was factor out an 8, 1/8, because all of them have that. If you go back and write this as an 8, that would be 4/8, right? So that would be times 3 minus 4 cosine 2x plus cosine 4x. Okay, if you brought the 8s on the outside. That's how they got their answer. And guess what? Those are perfectly legitimate equivalent answers. But yet, if we had been doing WebAssign, they were going to only look for one of them, and they would tell you all day long that was wrong. And it wouldn't have been wrong. It would have been right, okay? But you just didn't know which one they were looking for. I didn't know, anyway.
All you have to do is just keep
What's that again?
simplifying until you get down to.
Either one of those forms would have been fine. You know, we had it in the form they had it right before, the step right before. The simplify, you could have stopped right there. But they did it one more thing. It's no more simple than what we had, okay? Now, they said we can use a graphing utility to check the result. Notice that the graphs coincide. They did the first one as sine 4th x, okay? And the last one they did as 1/8, 3 times 4 cosine, minus 4 cosine 2x plus cosine 4x. And when you graph them both, they are on top of each other. That means they're the same function. That's equal to that. Okay. Good deal. There is a checkpoint there too. I would say well worth the effort to look at it. All right. You want to go any more? Next we get into half angle formulas. Okay. So I want to stop there? Okay. We'll stop there, and there, like you said, there is a bit more to go in this section. Not that much. We'll finish it, I think, on Tuesday week. Sorry, we missed class this Tuesday and this Thursday. When we come back after Honors and Awards Day, that next Tuesday, I won't see you for a whole week, you know. and then when we come back the next week, hopefully we'll finish the section. Do you want me to get your?
And we'll go into 6.
We'll go into 6, yeah. Now, do you want me to give you a copy of the test now, so you can work on it that week, or you want to just wait?
Yes.
You would, okay? Then what I'm going to do is